Welcome to part 4. This is the last of the special cases we'll be looking at, the case where the Q factor is much greater than 1. So here we have the poles as being omega naught over 2Q plus or minus omega naught over 1 minus 4Q squared all over 2Q. Right. When we've got a very large value of q, we can assume that 4q squared is much bigger than 1 and neglect the 1. That gives us the square root of minus 4q squared. That is, I could write that as the square root of j squared 4q squared, because j squared is minus 1 over 2q, which is omega naught over 2q plus or minus omega naught. Well, this is going to be j times 2q all over 2q. The 2q's cancel. We just end up with omega naught over 2q plus or minus j omega naught. In terms of an Argand diagram then, we've got two complex conjugate frequencies, there and there, where the real parts is omega naught over 2q and the imaginary parts is plus or minus omega naught. Now, this looks like this. With large values of q, we get a peak in the frequency response. And thinking in terms of the tent pole analogy, where I'm looking at the effect of both of the poles, I end up with this type of surface with two poles close to the imaginary axis, but with complex conjugate values. So if I just look at what happens along the imaginary axis, I get this type of curve, and if I plot this on a Bode plot by plotting it against the log of frequency rather than the linear frequency scale which is being used here, I would end up with this type of thing, which is the type of plot we've seen before, with the resonant peak at approximately the resonant frequency. On to the next type of circuit. Now, there's no reason we should take the output voltage across the capacitor. We could take it across the resistor. And in this case, I'm looking at the same sort of series circuit, but this time my output is the voltage across the resistor. If I do the standard potential divider analysis of this one, I end up with this expression, multiply through by j omega c, and I get this. Exactly the same denominator as before, but now there is a 0 at 0 hertz. In terms of q and omega naught, I could write it like this. The term here, the imaginary term on the numerator, is exactly the same as the imaginary term on the denominator. So in terms of q and omega, it would look like this. And I can rearrange this expression into this form. That's quite a useful form to answer the next question, which is, at what frequency does the maximum response occur, and how big is it? Bear in mind that we have here a standard response with a single 0 at 0 hertz. So it starts going up at 20 dBs per decade, hits the first pole, turns down by 20 dBs per decade, so it's now going horizontal, hits the next pole, so it turns down by another 20 dBs per decade, so it's now going down at 20 dBs per decade. At some frequency in between, there must be a maximum value, and it would be nice to know what that maximum value was and at what frequency it occurred. There's another interesting result we might want to know, which is, what is the 3 dB bandwidth of this filter? This is known as a bandpass filter. It attenuates low frequencies, it attenuates high frequencies, but it does give you a reasonable amount of signal at frequencies in between. So the 3 dB bandwidth, the bandwidth between this point here, where it's 3 dB down on its maximum, and this point here, where it's 3 dB down on its maximum, would be an interesting thing to know. Q factors of 10, the shape is different, but the questions are the same. What is the maximum gain? what is the 3 dB bandwidth, and at what frequency does the maximum gain occur? Right, to answer those questions we have to go back and look at our frequency response, and the frequency response is this form. So, this is our frequency response for our new series RLC circuit, and we're interested in what frequency does this have its maximum gain, and what is that maximum gain? Well, there's a shortcut for getting to that result, which doesn't require any differentiation, and it goes like this. Divide top and bottom by omega. J omega naught over Q omega naught squared over omega minus omega plus J omega naught. Right, and it's the magnitude of the frequency response that I'm interested in. So I'm interested in the magnitude of the numerator divided by the magnitude of the denominator. And for a maximum gain, I want the magnitude of the denominator to be as small as possible. Let's look at this denominator. This denominator, if I was to plot it on an Argand diagram, would have a real part of Q omega naught squared over omega minus omega, and an imaginary part of omega naught. And it's that distance that I have to minimize. But the thing is that for this circuit, omega naught is constant. It's just 1 over the square root of LC. So that imaginary component to this denominator is always the same. The only thing that changes with frequency is the real component. If I was to plot all the possible complex numbers that could happen on the bottom, on the denominator of this term here, they would all lie on this line. The imaginary part is always omega naught. The real part can be anything. Right. When does this resultant amplitude have its minimum value? Is it here? No. Is it when the real part is out here? Obviously not. Is it when the real part is back there? No. It's here. That is the minimum possible distance that you can go from the origin to any point on this kind of denominator line, on all possible values of the denominator for any value of omega. And it occurs when the real value is 0. The real value is 0 when omega squared over omega minus omega is 0, which is when omega naught squared equals omega squared, which is omega equals omega naught. So, in this case, our maximum value does always happen at omega naught. In the case of the first circuit we looked at, that was an approximation that was only valid at high values of Q. For this bandpass filter, it's always exactly true. The maximum amplitude of the output happens at the resonant frequency. And what is that maximum value? Well, we could just substitute omega equals omega naught back up into here, and we'd get J omega naught squared over, well, omega equals omega naught, so that term would disappear, over J omega naught squared equals 1. In other words, 0 dB. The maximum value that we get for any value of Q is always 0 dB, and it always occurs at the resonant frequency. The final thing of interest is, what is the 3 dB bandwidth of this circuit? Well, that does require a bit more tortuous maths. Here we're looking at the magnitude of the frequency response equals 1 over root 2, because that is where the 3 dB points will happen, when the voltage gain has dropped by 1 over root 2. There's a bit of a shortcut that we can use from this point here. When we've got omega squared omega naught squared over q squared omega naught squared minus omega squared squared plus omega squared omega naught squared equals a half, which comes from taking this complex term here and looking at the magnitude of it. It's just Pythagoras' theorem again. The square of the hypotenuse is the square of the real part plus the square of the imaginary part. I end up with this formula here. And for this to be equal to 1/2, this term here must be equal to this term here. So q squared omega naught squared minus omega squared squared must equal omega squared omega naught squared. And then if that's equal to that, we just have this over this plus this, which is just a half. Multiply out the brackets here and rearrange, and we end up with this formula here. It's a quadratic expression in omega squared. If you solve this quadratic for omega squared, you will end up with two possible values for omega squared, and therefore 4 possible values for omega. But only 2 of the possible values of omega are positive, and it's the 2 positive ones that we're interested in. It's tedious algebra to go through. If you're interested in the derivation, have a look at the short introductions. What's important is the result. And the result is that the difference between those two frequencies, the delta omega, the difference between the two frequencies at which it's dropped by 3 dB is equal to q divided by omega naught. That is a very simple result that comes out from the end of some rather unpleasant algebra. This is the 3 dB bandwidth of this bandpass filter, the difference between the two frequencies at which it's dropped by 3 dBs. So if the Bode plot was doing something like this, where this was 0 dBs, our maximum value, and this was minus 3 dBs here, then that range of frequencies here is q divided by the resonant frequency. The resonant frequency is right in the middle, where it has its maximum possible gain of 0 dB. Right, and that's the end of this one, I think. Yep. Next time we're going to carry on and have a look at some other RLC circuits.